Imagine a universe where the rules we know don't apply. Picture the most extreme cosmic objects, black holes, as something other than points of infinite density. This is the mind-bending possibility we're about to explore. A universe without singularities. For decades, singularities have been cornerstones of our understanding of the cosmos. They represent the ultimate breakdown of physics, points where gravity becomes infinitely strong and space-time curves infinitely. But what if this understanding is flawed? What if our cosmic theories need a rethink? The quest to understand our universe often leads us to question our most fundamental assumptions. The concept of singularities is no exception. As we delve deeper into the mysteries of the cosmos, we must be open to the possibility that some of our cherished scientific notions may need revision. The journey of scientific discovery is paved with the milestones of shattered paradigms. So let's embark on this intellectual adventure and explore the implications of a universe without singularities. To comprehend a universe without singularities, we must first understand what they are. In the realm of astrophysics, a singularity is a point in space-time where density and gravity become infinite. Imagine squeezing the entire mass of the Earth into a tiny point smaller than a pinhead. That's the extreme density we're talking about. These enigmatic entities are believed to reside at the hearts of black holes, those cosmic monsters that devour everything, even light, that dares to venture too close. As matter collapses under its own gravity within a black hole, it's thought to compress relentlessly until it reaches a point of infinite density, the singularity. Singularities are also central to the Big Bang theory, our best model for the universe's origin. According to this theory, our universe began from an incredibly hot, dense state, essentially a singularity, and has been expanding and cooling ever since. But this idea of a singularity, a point of infinite density, creates a conundrum for physicists. It suggests a breakdown of our current understanding of physics, as our equations cannot handle infinities. The notion of a singularity, while a cornerstone of modern cosmology, has always been a source of debate and skepticism among some physicists. The very idea of infinite density and curvature in space-time presents a profound challenge to our understanding of the universe. The skepticism has fueled the exploration of alternative theories that attempt to explain the cosmos without invoking singularities. One such avenue of exploration is loop quantum gravity, a theory that suggests that space-time is not smooth and continuous, but rather granular at the smallest scales, woven from tiny loops of energy. In this model, there's a limit to how much matter can be compressed, preventing the formation of a singularity. Another contender is string theory, which proposes that the universe is made up of tiny, vibrating strings of energy. String theory suggests that the immense gravitational forces at the center of a black hole would be spread out over a region, rather than concentrated at a single point, thus avoiding the formation of a singularity. These alternative theories, while still in their infancy, offer a tantalizing glimpse into a universe where singularities might not exist. If singularities don't exist, what does it mean for black holes? Without a singularity at their core, black holes might not be the infinitely dense, all-consuming monsters we imagine them to be. Instead, they could be something even more bizarre. Some physicists propose that black holes might harbor Planck stars, objects with a core so dense that quantum gravitational effects become significant, preventing further collapse into a singularity. These Planck stars would be incredibly small, billions of times smaller than an atom, yet contain the mass of a star. Another possibility is that black holes are fuzzballs, as proposed by some string theorists. These fuzzballs would be strange, tangled balls of strings, lacking a defined event horizon or singularity. Instead of being points of no return, fuzzballs might allow information to escape, albeit in a scrambled form. The implications of a singularity-free universe extend far beyond black holes. They challenge our very understanding of the universe's origin, the Big Bang. If the universe didn't emerge from a point of infinite density, how did it begin? One intriguing possibility is the Big Bounce scenario. In this model, our universe is part of a cycle of expansion and contraction. Instead of starting with a singularity, the Big Bang might have been a big bounce, a transition from a previous contracting phase to the current expanding one. Another alternative is the emergent universe scenario, where the universe existed in a static state before transitioning into the current expansion. This model suggests that the Big Bang might not have been the absolute beginning, but rather a dramatic transition in the universe's evolution. These alternative scenarios, while speculative, highlight the vast possibilities that open up when we move away from the singularity paradigm. The absence of singularities would have profound implications for our understanding of space-time itself. According to Einstein's theory of general relativity, gravity is not a force but a curvature in the fabric of space-time. Massive objects warp this fabric, causing other objects to move towards them. Singularities, with their infinite density, represent points where this fabric of space-time is infinitely curved, creating a hole in our cosmic understanding. But if singularities don't exist, then space-time might be finite and continuous, without any tears or holes. This could mean that our universe is finite in extent, like a sphere, rather than infinite. It could also have profound implications for the nature of time. Without a singularity at the Big Bang, the concept of a beginning to time itself becomes blurred. Perhaps time, like space, is finite and cyclical, or perhaps it extends infinitely in both directions. Beyond the realm of physics, the concept of a singularity-free universe carries profound philosophical implications. For centuries, the idea of infinity has captivated philosophers and theologians alike. It represents the ultimate, the unknowable, the beyond comprehension. If the universe is indeed finite and singularity-free, it challenges our very notion of limits and boundaries. It suggests that even the most extreme phenomena in the cosmos are governed by laws and principles that we can, in principle, comprehend. This realization could lead to a paradigm shift in our understanding of our place in the cosmos. It suggests that we are not insignificant specks in an infinite and indifferent universe, but rather integral parts of a finite and interconnected whole. The quest to understand whether singularities exist or not highlights the frontiers of our current knowledge. We are peering into the deepest realms of the cosmos, probing the very fabric of space-time, and questioning the fundamental nature of reality itself. The answers to these questions remain elusive, hidden behind the veil of our current technological and theoretical limitations. However, the pursuit of these answers drives scientific progress, pushing us to develop new tools, theories, and ways of thinking about the universe. Whether singularities exist or not, the very act of questioning their existence expands our understanding of the cosmos. It reminds us that science is not a static body of knowledge, but a dynamic process of exploration and discovery, a journey into the unknown that is both humbling and exhilarating. The possibility of a singularity-free universe invites us to contemplate our place within it. It challenges us to move beyond the familiar and embrace the unknown, to question our assumptions and to remain open to new possibilities. In a universe without singularities, we are not confronted with points of infinite density and breakdown of physics. Instead, we find ourselves in a cosmos governed by laws that, while complex and still not fully understood, are within the realm of human comprehension. This realization can be both empowering and awe-inspiring. It reminds us that we are part of a grand cosmic tapestry, woven from the same fundamental forces and particles that govern the evolution of stars and galaxies. In a singularity-free universe, we are not insignificant specks, but integral participants in the grand cosmic drama.